In this problem, we've mounted a giant spring gun to a cart. The spring gun has a constant of 120 newtons per meter. We squish it by 2.5 meters to load it. And so, of course, we're putting energy into the system when we do this. We then use the spring gun to shoot a bowling ball off to the left. It's a 5-kilogram bowling ball. And we're using the recoil of the gun to accelerate the car. So this is really just a momentum explosion problem. We have the total amount of energy in the system. I have nearly frictionless wheels, which means I don't have to worry about any external force acting horizontally on this system. And that means momentum is conserved. So we have the unknown final speed of the bowling ball, unknown final speed of the cart. We're going to express equations for the total energy and the conservation of momentum, and we should be able to solve for those two unknown speeds. That's actually what we're asked for in part B. So we begin by getting the total energy stored in the spring, and that's a 1/2 kx squared. And the spring constant's 120 newtons per meter, and the compression distance is 2.5 meters. And this gives me 375 joules of energy stored in that spring. Then we look at conservation of momentum. And in the initial state, the total momentum was 0. So in the final state, it still has to be 0. And if you want, you could include directions on these velocities by using signs. So I could put a minus sign in front of VB. But my preference here is to just say the magnitude of leftward momentum has to be equal to the magnitude of rightward momentum in order to guarantee that the vector sum is 0. So I'm just going to say the mass of the bowling ball times its velocity. It's got to be equal to the mass of the cart times its velocity. So my leftward momentum equals the rightward momentum. That means the vector sum of momenta is equal to 0. So there's that piece. And then the second equation that I want is the one that expresses the total energy in these two objects. So the energy was originally stored in the spring, but in the final state, it's in the kinetic energy of these two objects. So I have 1/2 mass of the bowling ball times the speed of the bowling ball squared, plus a 1/2 mass of the cart, speed of the cart squared, has to all add up to 375 joules. Now we can just plug numbers in and solve the system algebraically, and we should be able to get our final speeds. So the mass of the bowling ball was 5 kilograms. Again, the speed is unknown. The mass of the cart is 22 kilograms. The speed is unknown. And we also plug the masses into the energy equation. Now to solve this system, we're going to use substitutions. What I do is take the first equation and solve for one of these speeds, and then I'll plug it into the energy equation, leaving me with only one unknown. So I'll go ahead and solve for VB in terms of VC. So VB is 22 over 5 VC, and that's 4.4 VC. And then we sub that into the energy equation. So this is going to give us a 1/2 times 5 times 4.4 VC all squared, plus a 1/2 of 22. That's 11, but I'll leave it that way for now. 1/2 of 22 times VC squared is equal to 375. So we can factor a VC squared out of the left side and combine all the constants. So I just take 1/2 times 5 times 4.4 squared, and then add 1/2 of 22, which is 11. And this gives me 59.4 VC squared is equal to 375. And so we divide by 59.4 and square root the result. Into 3 sig figs, I get the speed of the cart is 2.51 meters per second. Now we just go back to our original substitution. VB, the speed of the bowling ball, is 4.4 times the speed of the cart. And I actually kept a little extra precision in my calculator, and this comes out to 11.1 if we round it to 3 sig figs. So 11.1 meters per second for the speed of the bowling ball. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.